welcome to the lecture of this finite volume method. Now, moving ahead, we may look at one more important topic, is that anisotropic diffusion. So, we have done some discussion on this when we are looking at the variation of the diffusion coefficient gamma over space and cell to cell. When there is a variation, we have looked at it, but now we are looking at it in more details. So, what it happens is that if there is a anisotropy in the diffusion coefficient, our semi discretized equation, so the semi discretized diffusion equation, that will look like now f equals to all these places minus gamma dot del phi f. Here one can think about this gamma is like an dot SF equal to SC BC. Here gamma is varying in space. So, what happens, this gamma here can be treated as, this is also a second order symmetric tensor, which will actually represent the anisotropic tensor. So, now if you assume a general, so assuming a general 3D situation, so which can be boils down to 2D and 1D. So, what one can write this left hand side, if you assume a general 3D situation, the left hand side, which is essentially minus gamma dot del phi at phase f dot SF, which will be essentially looking like an tensor, which will be gamma 11, gamma 12, gamma 13, gamma 21, 22, 23, gamma 31, 32, 33 at f. Here you have del phi by del x, del phi by del y, del phi by del z, phi dot SF. So, the in a 3-dimensional system, generic 3-dimensional system, gamma is an tensor. So, the gamma would look like that. So, if you do the matrix calculation, what you get, minus gamma dot del phi at f dot SF equals to minus some gamma 11 del phi by del x plus gamma 12 del phi by del y, gamma 13 del phi by del z. Second row is gamma 21 del phi by del x, gamma 22 del phi by del y plus gamma 23 del phi by del z, 31 del phi by del x, 32 del phi by del y, 33 del phi by del z, and you have Sx, Sy, Sz at phase f. So, that is also the component of this surface vector SF. Now, if you do further manipulation, this would give me back del phi by del x, del phi by del y, del phi by del z at face F into, write down that 1 1, 1 2, 1 3, 2 1, 2 2 gamma 2 3, 3 1, 3 2, 3 3 at F, Sx, Sy, Sz at F, which further simplification can get me minus del phi F dot gamma transpose dot SF, which is, one can think it is del phi SF dot S prime F. So, if you substitute this particular expression in this particular equation, so now if you substitute that one there, what we get is summation of faces minus del phi F dot S prime F QC BC. So, this is what you get as semi discretized system. Now, one can expand this one and get the full discretized system from here. Now, one can simplify from here that gamma to, if you apply instead of tensor to be 1 and S F prime equal to S F, so the same thing can be used for both isotropic discretization and anisotropic discretization. So, this is the special case for isotropic diffusion. So, again reiterating that fact, the beauty of this finite volume lies here. You see a generic expression for the diffusion which contains the anisotropy. Now, from anisotropy, if you just replace them with this coefficient, that will bring down the whole system to a isotropic diffusion system, and which is again a special case of anisotropic diffusion system. So, that again ends or closes the thing in that a fashion, such a fashion that if you have a generic equation derived for a generic system, like when we derive the discretized equation from non-orthogonal unstructured system, the special case is the orthogonal system. The cross diffusion goes away and we can get back the non-orthogonal system. Again, when you consider the diffusion, anisotropic diffusion, the isotropic diffusion is one special case, and one can always achieve things from there. Now, the part which actually would like to discuss is that now we got this discretized equation. For the solution, there are some iterative process which are involved, and there you need to do some sort of a relaxation, whether it could be under or it could be over, depending on the situation. And why that happens? That happens essentially your any genetic variable, that phi. So, the gamma, so the gamma is a function of phi, and also it can possibly happen that you have a non-orthogonal grid. So, if you have a non-orthogonal grid, which actually means you have a cross diffusion term, or rather large cross diffusion term or contribution. So, if you have a non-orthogonal grid, then you have a large cross diffusion term. So, if you have a large cross diffusion term, again it will have a large variation in phi. So, it actually getting towards a system where you have a non-orthogonal grid, which actually leads to some sort of a large cross diffusion term. Large cross diffusion term lead to a large variation of phi. So, which means large source term, and which may possibly, if you have a large source term, which can possibly the leads to some sort of a divergence. So, that means the code can be unstable and it can be a divergence. So, this is essentially related to your linear solver, where it can be diverged. And why that happens? Primarily because of all this. If you have a very skewed or non-orthogonal grid, which can lead to some sort of a cross diffusion term. Cross diffusion term can lead to large variation of the variable across the cell, large variation lead to the source term or steep source term, which can lead to the divergence of the solver, and that essentially one can think about due to non-linearity of coefficients and cross diffusion term. So, due to that primarily happens. So, what is the remedy? Remedy here is that since that happens and all these diffusion equations, they are kind of lead to a system where one has to solve the linear system. So, this becomes an pertinent issue or pertinent problem, though we will come back and discuss. This is a part of our discussion of linear solver. When we talk about the linear solver, we will do the discussion, but since some understanding of this kind of situation is required, we are doing the discussion, preliminary discussion here, so that you can appreciate what can happen in non-orthogonal system, which leads to this large cross diffusion term and lead to this kind of situation. So, one has to do two things, mostly basically in order to promote convergence, one has to convergence as well as stabilized the solver. So, one has to do some sort of a under relaxation of variable. So, you need to slow down. So, which means essentially slow down the changes of variable phi. So, that means when you go from one step to another step and another to another step, so you slow down the variation or the changes, so that you move towards your final solution slower. It is not with 100% weight you update the solution and move from one step to another. So, this is called under relaxation, and that is very much required in order to have better convergence and also to have a stable system. So, once one can look at the general discretized equation which you have AC phi c plus F NBC AF phi f equals to BC. So, this is true for any system what we have discussed so far: orthogonal, non-orthogonal, non-orthogonal, unstructured, orthogonal, Cartesian, everything, non-Cartesian, orthogonal. This is a unique equation that works for everybody. Now, while doing this iterative process, one may do some sort of an algebra and can write from there phi c equals to, one can write like minus f goes over all this A f phi f plus B c divided by A c. So, let us define phi c star, which is value of phi c from previous iteration. Okay. So, phi c is added to or subtracted from the right hand side of this equation. So, phi c star I can add or subtract. So, let us see, I will do the addition, then I will have minus A f phi f plus B c, where f goes N B c A c minus phi c star. So, I have just done a from here to here, one hand I have added phi c, subtracted phi c. Now, if you look at this expression within the parenthesis, it is essentially represents the change in phi c produced by the current iteration. So, essentially the element or the value within this parenthesis, this shows the change in phi c produced by this current iteration. Now, one can write by introducing another extra variable called lambda, and I can write down this particular equation phi c equals to phi c star plus lambda, and I will write everything within this parenthesis like that, which is A f phi f plus B c divided by A c minus phi c star. Or one can do A c by lambda phi c plus summation of f goes to N B c A f phi f equals to B c plus 1 minus lambda into phi A c 1 minus A c lambda phi c. So, that is what it turns out. Now, here you get an expression which one has to look at it carefully. Now, when at convergence phi c is actually become phi c star when the system is converged. So, if you have converged, then they will become phi c equals to phi c star, and value of the relaxation factor, it will become actually independent of this relaxation factor lambda which is used. So, this you can see from this equation what. Now, another thing is that depending on the value of the lambda, one may have, if lambda lies between 1 to 0, this is called under relaxed, or if lambda is greater than 1, it is over relaxed. So, depending on the value of lambda, one can have a system which is either under relaxed or should be over relaxed. So, most of the time actually in normal CFD calculation or most of the CFD calculation, the under relaxation factor is used because that leads to a, but it is also not very generic that always you need to use under relaxation. It all depends on the particular equation or the physical problem that one is solving for. Now, that having said that, a value which is lambda close to 1 implies that you need very little under relaxation, okay, or close to 0 means you have heavily under relaxation. That means someone is talking lambda equals to 0.001, that means your system is heavily under relaxed, and someone is using lambda equals to 0.99, which is almost close to using very little under relaxation. Now, the optimum under relaxation factor is problem dependent, as I said, and is not essentially governed by any generic rule. So, which means, so lambda or the value of lambda value depends on problem and it is not governed by any general rule. So, the factor which affects lambda values include the type of problem solved, as I said, size of the equation system, that means number of grid point, degrees of freedom, grid spacing and all the other iterative procedure. So, all these are the issues which will be involved in choosing the value of lambda. Also, lambda is essentially assigned, or how one can choose this lambda value. It also depends on, to some extent, the depends on experience of user, because this is heavily dependent on your problem definition in your computational grid, degrees of freedom, grid spacing, iterative solver and all these things. Moreover, it is not very necessary to use the same under relaxation value throughout the computational domain. So, one can actually also vary a different value of under relaxation at different location in domain. So, that is also possible, and the lambda can also vary iteration to iteration. So, that means from one physical time step to another physical time step one can vary the lambda. So, to promote better convergence or stability, also different locations one can use different values of lambda in the domain. Now, this equation if we rewrite in a slightly different form, so my AC, which one can say AC by lambda, and the source term which is added as BC plus 1 minus lambda divided by lambda AC phi C star. Now, this particular method of under relaxation plays a very key role or important role in stabilizing the solution of non-linear problem. So, that means what we see here that the different kind of lambda can be used. The lambda can be varied from iteration to iteration, and then once we use this kind of under relaxation, that actually whether depending on lambda though under relaxed or over relaxation, the system can be used in more stable fashion. The iterative solver can be converged, or solution, the solution of iterative process can be improved, or maybe can be made faster, number 1. Number 2, solution of the iterative process can be stable. So, the discretized equation or the governing equation, they do not get unstable, or the linear solver does not get unstable. So, it can be also solved stably. So, these are things which are essentially important when you talk about the solution of this iterative process, but this is just to give you an idea. When you have the discretized diffusion equation like this, and then what kind of iterative process one can use and what are the certain issues, but more detailed discussion will follow while we will be talking about very specifically on linear solver. So, now that brings down to the important discussion that what we have done while talking about the discretization of diffusion equation. What we have considered here? We have considered here the steady and with source. So, that is what we have done, and the way we have approached to that, first we have looked at a simplest system, that means first Cartesian orthogonal system. Then from there, while we are talking about the orthogonal system, Cartesian orthogonal system, we have talked about Dirichlet boundary condition, the implementation of Dirichlet boundary condition, Neumann boundary condition, mixed boundary condition, symmetry boundary condition. So, all we have done. Then the system we have taken is the non-Cartesian orthogonal. So, still the orthogonality is maintained. So, this is a one step improvement, and same thing we have repeated. We have looked at the implementation of boundary condition, because essentially from here the discretization process will actually give us back a discrete equation which is in a generic form. That means this gives us back the equation of AC phi c plus f NBC AF phi f equals to BC. That is the generic equation that we get. So, when you talk about the non-orthogonal, we have done that. Then finally, you got non-orthogonal unstructured. Here also we have done the detailed discussion of this implementation of the boundary condition. So, that is where things were. When we talk about the non-orthogonal system, we came across the important term cross diffusion term, which is a important contribution, then skewness, and then finally for this we have talked about the iterative solution process or the convergence and the stability of the process. And the non-orthogonal system is one which is essentially, if you go back in this direction, this is a generic case and the special case can be obtained in all these direction. So, non-orthogonal with a special correction can get you back the simplest on the orthogonal same. So, we will stop here and then the other discussion will follow up in the next lecture. Thank you.